This is a review of Unit 2. And for the biochem students, it's probably less than timely. And for the Chemistry 100 students, this is ahead of the time. You guys still have another week before your exam starts. So if anybody has any pressing questions, we can get to that first. Otherwise, what I'll do is I'll start with chapter 5 and just kind of cruise through it, and then you stop me if you have any questions. But first, anybody have any questions just offhand on anything? I guess that means no. So what I'll do is I'll share the screen and just go through chapter 5, is it? So again, red box stuff isn't on the exam. So periodic law was basically how they put together the periodic table. So a very pragmatic way of doing it. Just what are the chemical properties and which chemical properties repeat themselves? And then they just put everything underneath each other so that pragmatically, if you're in the same group, an element is going to have similar properties to another element. So periodic law is just that, properties repeat themselves periodically. So then we talked about metals versus non-metals, the different ways to organize and discuss the periodic table. These are representative elements. These are the non-representative elements over here. This line right here represents the distinction between metals and non-metals. And then we have metalloids with the properties of both right there on that line. And then there were several questions. Why do non-representative metals not obey all the rules? Because what we learned in chapter 8 is these are the noble gases. That's why the little happy face there. They're already happy. So if you're here, you want to get here. If you're here, you got to go backwards to get here. But if you're over here, there is no way that you're going to be able to gain that many electrons or lose that many electrons to become like a noble gas. So you have to do things differently. So let's see. These are the groups that you need to know the names of. Then you notice in Unit 3, we're using electronegativity. So electronegativity is an important thing for you to understand and be able to use. It's the ability of an atom to pull electrons towards itself in a bond. So let's see. And that's about it. So any questions on chapter 5? Okay, so maybe we'll go to chapter.
I actually have one question.
Yeah.
For the elements in the middle of the periodic table, and they have 7 and 8 electrons, like 8 valence electrons. I still don't understand why that isn't considered stable if they have 8 valence electrons.
Because they're not S2P6. They might be S2D6, for example. So now
instead of the full 10.
It's not completely full.
Okay.
Yeah.
Okay, I gotcha.
Then, apparently everybody likes balancing nuclear equations. So going through radiation, this was the classical radiation, alpha, beta, and gamma. Then as time went on and they figured out more and more, then we find that pretty much everything that we know about comes out of stars and is cruising around in space and is known as cosmic radiation. Here's an electron. Here's a positron. The electron is considered matter. The positron is considered antimatter. Ionizing radiation does exactly what it says. It causes an electron to be ejected. In other words, you're ionizing a molecule. So as an example, I went through the ionization of water. I could have used your DNA right here. And that would have been a problem for your DNA, right? So cosmic radiation, all ionizing radiation can be dangerous. I had to do a calculation with this on the homework. I think that's enough. You don't need to do it on the exam. Otherwise, you're just kind of memorizing an equation. But here's the gist of why it turns out that way. Okay. So these are not dosages. These were the original ones that we used to measure radioactivity. And they didn't really realize that this was just a huge amount of radiation. So I remember when I was working with radioactivity, we would be ordering picocuries of radioactivity. Remember, nano is 10 to the 9th, right? Pico is 10 to the 12th, minus 12, I should say. And these are not dosages. These are dosages. Notice it's the energy absorbed per kilogram of tissue, also known as a RAD, radiation absorbed dose. So these are also dosages. And of course, dosage is extremely important in biology. When it comes to completing nuclear reactions, you have a lot of examples in here. And so I went through these simple ones over here. Let's see. And then a bunch of practice. Now the answer to these is somewhere in the chapter. And I went through how you could do it. You could do it a different way. It's just like balancing an algebraic equation, right? There's more than one way to do it. But I guess the major thing is that the subatomic particles are always the same. Here's what they are. So you can't go around just inventing your own. Let's see. And then the types of nuclear reactions. So I took it upon myself. I mean, you're not going to be able to go Google the 6 types of nuclear reactions because it doesn't exist. So I just did this because I think it's a good way to learn it. So radiation, here's an example of positron radiation, right? Fission, a big nucleus breaks into smaller ones. It may also have radiation at the same time. Then bombardment is when you have 2 things on the reactant side. So the idea is that here's an aluminum just sitting there minding its own business, and somebody purposely is slamming it with a neutron. And this is not spontaneous. Somebody's doing this. So here's bombardment, also known as neutron capture, because for a while nothing happens. Here's bombardment producing radiation. Here's bombardment producing fission. Bombardment producing new elements. But I put it all in the category of just being bombardment. An electron capture happens spontaneously within the atom itself. So every so often, an electron close to the nucleus basically gets sucked into the nucleus. When it does that, it combines with a proton and they form a neutron. So notice that with potassium, and this is part of itself, right? So this is not bombardment. So notice that one proton disappears. So now you change the number of protons so that you have a different element. That's a transformation, right? But the number of things in the nucleus, which is protons and neutrons, doesn't change. You're just taking a proton and changing it into a neutron. Online, you might see this stuff, and it's just like totally bizarre. It's like, if you don't know anything, it's like you're trying to learn it, that's just going to confuse you. Then fusion is when smaller nuclei fuse together to form a larger one. Then transmutation is simply the number of protons change, and that changes what the element is. In half-lives, here's the equation that describes a half-life. For one half-life, if n is equal to 1, for example, you're simply taking the mass that you have to start with and multiplying it by 1/2, which is the same thing as dividing by 2. So how I generated this curve right here is simply going through half-lives. So here's the easy way to navigate doing the mathematics here, which is not a direct proportion. This is an exponential decay. So here's the equation for an exponential decay. But the way for us to easily navigate that is simply, here's your starting, and every time you have a half-life go by, you just cut it in half. Okay. So after 4 half-lives, there's only 6.3 grams. And later on, you can convert the half-lives into years. And that is a direct proportion. That's simply conversion factor. Okay. So here are several problems about that. I don't know if you have any questions about any of these. Yes, we have radio stuff in our lives all over the place. All the imaging that we do and everything. Of course, that saves lives, but it also increases our exposure, to ionizing radiation. Then we talk about nuclear fuel and bombs. So the reason why terrorist countries don't have nuclear bombs is simply because the technology is just too incredibly difficult. Let's see. Oh, that's it. So any questions at all on Chapter 6, Nuclear Chemistry?
So for like the nuclear reactions, is it kind of just like we're just kind of doing math? We're kind of just adding up and subtracting from like nucleus and like electrons and stuff?
Yeah, and
In a
you're
sense.
also using your knowledge of radiation and using the periodic table, right?
Yeah, yeah.
Chuck Norris. Okay, so I wish I had time to go through Chapter 7. I haven't even updated it for about 2 years. Okay, let's see.
Can one nuclear reaction be more than like one type?
Yes, most of them are. Most of them are, and that leads to the confusion. So what I'm trying to get you to think is like, okay, here's 7 things. You can take one nuclear reaction, and that nuclear reaction may be describable using 4 of those 7 things.
Wait, what do you mean by that, Professor?
Well, like we looked at bombardment of uranium-235, for example, and that bombardment causes fission to happen. It's also a transformation, and it also causes radiation to happen. So that one particular nuclear reaction is describable by 4 out of the, or at least 4 out of the 7 possibilities, right?
Gotcha.
But it's not any different than you. I mean, you're a student, you're a person, you're a male, you know, all that kind of stuff, right? So we're just describing things. Okay, so chapter 8 causes a lot of confusion because light is confusing. It's just not in our everyday experience. So here's ocean waves diffracting. Who would ever think that light would do that? But light does do that. So it has wave particles, it has wave properties, and it also has particle properties. By the way, the theoretical particle of light is called a photon. And it has probably close to 0 mass, if any mass. But theoretically, it does have mass. If you talk to physicists, which I don't normally talk to them, I usually argue with them. It's just like, so what you're telling me that every single particle that we've discovered so far has mass, even the neutrino, which is way heavier than a photon, has theoretical mass. Why would you try to tell me that everything else in the universe has mass that comes flying out of a star except for light? Why would there be such an exception? Anyway, they get all flustered about it and everything. They talk about their mathematical calculations, and then I bring up the concept of significant figures and uncertainty. And then they get all irritated with me. So all the things that we're talking about, like say we're talking about an electron in the 2p1, right? All that is really not a place, it's an energy. So here would be 0 energy. If I take the electron out of the nucleus and move it out here, I had to put energy in there to do that. So the farther from the nucleus, the higher the energy. So the 2p shell, subshell, whatever, is a higher energy than the 2s. So yes, you should be able to figure out what's valence electrons, what's core electrons. And of course, the valence electrons are given to you by the group number. So the shell is simply a general volume, but the shell, which is really the principal quantum number, given the symbol n, tells us the maximum number of electrons that you can put into a shell. It also tells us the number of subshells that are possible. Then an orbital is the most specific place where you're going to find electrons. So here are the subshells, and again, we need only 4. Here's the number of orbitals in each one. You can see that's a mathematical progression. So is this, because the maximum number of electrons is simply 2. So an orbital can have 0 electrons, 1 electron, or 2 electrons. If it has 2 electrons, those 2 electrons have to have opposite spins. And here's just a symbol showing you that the shapes are different. Okay. So all those drawings and everything else that we have in our figures, those are the solutions to the Schrodinger equations. So here's a mathematical progression. So shell number 1, 2, 3, 4, all the way through 7. Here's all the different shells over here, right? 4 and 5 were taken out of here. And then shell number 1, I can have one subshell. What is it? It's going to be an S because that's the lowest energy. How many can I get into an S? Only 2. Now it's full. So that's close to the nucleus. It's full. Then shell number 2 has up to 8 electrons into it. And that's so much that it starts to split into subshells. So an S and a P. Like shell number 4, it can be split into 4 different subshells. So you just got a lot of electrons in there. So here is shell number 4 showing you the location of it. And then this order right here is what we find on the periodic table. Notice we go 3s2, 3p6, 4s2, and then 3d1 through 3d10. Why does the 4s come before the 3d? Well, because it has lower energy. So how do we match that? We take that same thing that we built up there and we simply take the diagonal. When that happens, the 4s comes before the 3d. So this is the order that we see on the periodic table. That's the Aufbau principle. We will use that for all electron configurations. And again, the 4s is a completely different animal than the 3d. The orbitals are different shapes, and please don't think that all orbitals are spherical like an S, because they're not. So I tried to explain that a couple of different ways. Here, if I treat them all as spherical orbitals, you see that you have this orbital overlapping, because these electrons right here repel one another. So the more electrons that go into a shell, the bigger the shell gets, and it starts to spread out and bulge into other shells. Here's another concept of that. Regardless, if you look at the energy over here, 4s is a lower energy than the 3d. So then we talked about several different things about electron configuration. So the immediate source of confusion is you go to the periodic table and you see these electron configurations on the periodic table, and you want to be able to just copy them down. But you can't do that because it's not in the Aufbau principle. It's simply doing this. And the reason why it's doing that is because it now helps you find out which are the valence electrons. So for example, if you go to bromine, here's bromine. Do this. So bromine is in group 7. So it's got 7 valence electrons. If you look at the periodic table, look, they're split up. Valence electrons in the highest numbered shells. So that's shell number 4. So here are the 7 valence electrons. But if you look what they did on the periodic table, because they didn't use the Aufbau principle, you can pick out right away which are the valence electrons. Then we can write it as the complete or total electron configuration. We can write it as noble gas abbreviated, or we can just say, what is the generalized group? For example, in group 7, all of them behave the same. I mean, not exactly the same, but why do they have such similar behaviors? Well, because they have the same number of electrons in the same subshell. That's why. So here's group 2, right, with magnesium. So here's total electron configuration, the noble gas. So how are the two valence electrons arranged? Well, they're in s2. Here's radium, also in group 2. It's also arranged in s2. So what does an element in groups 2 do? It does the same thing that any element would do if it started off as being two valence electrons in an S-type of subshell. So I gave lots of examples. So here's nonmetals, here's noble gases, and the representative elements react in order to get the noble gas electron configuration. They obey the rules that we've been talking about. So metals like, representative metals just simply lose all of their valence electrons. There's no dots around them in the electron dot configuration. Nonmetals, no matter how many they start with as an element, they gain enough electrons to become like a noble gas. So in Lewis dot formulas, they will gain electrons until they have 8. That represents S2P6. So, yeah, what we're learning, you're looking at it in like with a telescope, right? You're looking at a small portion of it, but that's what we really have to do, is to learn small pieces, and then eventually we see that the whole thing works together as a system. Let's see. So the non-representative elements are not always able to reach the noble gas electron configuration. So that means we cannot really understand their behavior. And if you look really closely, we can. But if there's no way you're ever going to be electronically stable, what are you going to do? One strategy is you simply don't do anything. You simply become unreactive. Because reacting with something doesn't get you anywhere. And another strategy is you simply oscillate back and forth between quasi-stable forms, like what iron does between +3 and the +2. So the non-representative elements may not obey all the rules, but they still lose valence electrons in their highest numbered shell. So yeah, this was the most difficult part to do. So how do we know what they're going to do if we can't predict what they're going to do? Well, that's where it's useful to look at the oxidation numbers. So if you look at chromium, for example, chromium is one of those metals that has no way of getting to be like a noble gas. So how do we know what it's going to do? Well, it has the oxidation numbers right there. It starts off with 6 valence electrons. If it forms a +2 ion, it still has 4 valence electrons. If it forms the +3, then it still has 3 valence electrons. And there are exceptions to everything. So there's exceptions to the Aufbau principle. Unfortunately, it happens right in the transition between where the f orbitals, subshells start to come in. So people look at that and they're all confused. It's like, well, look at that. It's just a mess right there. I don't understand anything. It was originally based upon the Aufbau principle. So if you look at the Aufbau principle, it goes in a nice, consecutive, understandable manner. If you look what's on the periodic table, it's totally confusing because those are exceptions to the rules. Red box, you don't have to explain it. Then orbital diagrams, okay, all we're doing is taking advantage of the 4th quantum number. So for example, if I say 1 So you must get a better idea. Say I designate some electrons in an atom as 4f3. What does that 4 stand for? That's the shell. That's the first quantum number. What does the F stand for? Well, that's the subshell, about the second quantum number. And then which subshell is it in, or how many electrons are there? That really is the third one, but the fourth one is in which orbital is it in? And if that's the case, what does it spin? So the spin-spin quantum number is the fourth quantum number. And that's why we need the boxes. Okay. So if I say that there's 4f3 and I draw this and I put 1, 2, 3 electrons in there, that means that they could be the upspin or the downspin in either case. But that's still taking advantage of only the 3 quantum numbers. The fourth quantum number is it spinning in the up position or the down position? So this is allowed because they're paired. This is not allowed because they're not paired. All of this is allowed. And this is where I really get irritated sometimes with my fellow chemistry professors. They'll say, oh, this is bad. That's bad. You have to go here and then here, then here. No, you don't. Electrons don't have to follow rules that you as a human make up. They just do what they do. But these 3 boxes represent the 3 orbitals in a p subshell. So here I have 1 electron to go in here, and I got 1, 2, 3, 4, 5, 6 places that are all of equal energy. That's why it doesn't matter where you put that one. So when we do box orbital diagrams, all we're doing is the same thing that we've always done, except now we're adding boxes, providing the spins of each of the electrons. So let's look at chromium here. So here is the noble gas shorthand method for chromium, right? And so here's an S. S has only 1 orbital. There's 2 electrons, so they got to be paired. Here's a D. It's got 5 orbitals. I have 4 electrons to go into it. You know what? I can put them anywhere in here, and they can have any spin they want. So what happens when chromium forms the +3 ion? I got to take 3 electrons out of here. If I take these 3 over here, what I just did is I avoided the idea that this is the highest numbered electrons. This is the highest numbered shell. So if I'm going to take 3 electrons, I'm going to take this and make it completely empty. Then I'll have to take 1 out of here somewhere. Doesn't matter which one. If I'm going to form the +6 ion, then I'm taking all of these valence electrons out. If I'm going to form the +2 ion, look at this. What if I took 2 from here? What does that do to give it stability? Nothing, because it's still left as being partially filled. So again, I would take it from the highest numbered shell, and then this doesn't change. But at least now this is completely empty. In chromium, the element, which is fairly stable, by the way, that's completely full. The only difference is now it's completely empty. So I gave a lot of examples over here. Does anybody have any questions about any of these examples? By the way, I do go through some difficult ones here. And my idea is that if you can understand the difficult ones, you'll be fine on the exam. That's the whole purpose. Do well on the exam. So the rest of this chapter is I'm trying to give you an idea of where all this stuff came from. It just seems so convoluted, so complicated, but yet it comes from a natural progression of understanding light, how light is absorbed by atoms, how light is emitted by atoms, because we can figure out the energy of light by either its frequency or its wavelength. So I talked about what is electromagnetic radiation. By the way, is there electromagnetic radiation coming from electrical wires? What do you guys think?
No.
What are EMFs? People are always talking about, oh, the power lines are dangerous because they're giving you EMFs, and cell phones are dangerous because they're giving electromagnetic waves into your brain, causing brain cancer.
I was actually going to ask you about that, about the cell phones.
Yeah, now all these people are against 5G. It's like,
Yeah.
what is this 5G? We had 4G. 5G is just a little bit better, okay? So, but they think it's some kind of a plot to take over America by the deep state and all this kind of stuff. It's like, it's just an advancement in technology. And the answer is yes. Power lines do give off EMFs, electromagnetic fields, which is a form of radiation. But they don't travel far and they don't do much damage to biology. Do they possibly do some? Possibly. But as far as we can tell, it's safe.
How about our cell phones?
You know, the most dangerous thing on a cell phone is social media.
So there's no radiation that comes off of our phones?
Oh, there is, but it's just minimal. Very minimal.
Like, what would you compare it to, like a radio wave?
Well, you know, we're being bombarded by so much radiation and everything else all over the place. It's like your cell phone is just like a small, infinitesimal amount compared to what you're bombarded with anyway. But sure, it's all cumulative.
Yeah.
You know, but if you want to, you know, go into what's called a Faraday cage and live your life in there, and you know, because you want to live longer or something like that, it's like, okay, that might make you live maybe half a day longer. Your life will be terrible. So I had you do these kind of calculations on the homework. I won't bother you with that on the exam, but it is rather interesting to see how, oh my God, this is simply constants, and the units simply cancel out, and energy has the units of joules. So here is the basic idea, and yeah, you should know that gamma rays are more powerful than, say, infrared and radio waves. That kind of stuff you should probably know. So where the data comes from is that it was the photoelectric effect. And the photoelectric effect told us that, okay, I look at a metal which doesn't hold on to its electrons very tightly. So it's very easy to make a current happen in metal. And I shine light on it of a certain wavelength, nothing happens. I change the wavelength, something happens. I make a stronger wavelength, nothing happens. If I go back to that wavelength that caused the photoelectric effect and I simply put more photons of that same energy, then it causes more current. So it's not the power of the light, but it's the frequency. So that frequency is being able to be absorbed by the electrons in the atom. The other frequencies are not. So that's absorption. What about emission of energy? So I heat something up and it gets red hot, maybe white hot. So if it's a solid, we get these continuous spectrums. And the idea is that it's like being in a mosh pit. So you're right up against each other in a solid, so you're bumping into each other all the time. So there's so many different ways to get rid of that energy that you end up being able to pretty much go through the entire visible spectrum. So you get a rainbow, a continuous spectrum. But if you do it to a gas where the particles are far apart, they're not bumping into each other. The only way for that electron and this atom to get rid of that energy is internally. So that's what we mean by quantize. That's what we mean by quantum numbers. So the light, or the transition between different places, the ground state and the excited state, is only a certain energy. So if I have this electron absorb this much energy, okay, only this much energy can be absorbed. And when it gives off and jumps back down here, only that much energy is given off. That represents one line on the discontinuous spectrum. If it jumps up to here, now it could come down stepwise. It could come from here to here and give off another wavelength, here to here and give off that same wavelength, or it could come directly from here to here, give off energy represented by this amount of energy, which might be this one here. So light energy is absorbed and emitted from atoms in a quantized way. But then I went into the different kinds of light: incandescent, fluorescent, LEDs. Now, again, this is all in red boxes, right? So then what will be on the exam is Lewis-Dot formulas. So Lewis-Dot formulas, we're looking at it in this chapter only for elements and ions. In Unit 3, we're using that same mentality, that same concept to decide how molecules are put together. But this is a very good separation because you understand this before we start on the other more complicated stuff. So it's very simple. Whatever group you're in, if you're an element, no matter what group you're in, that group number tells you how many dots, because that tells you how many valence electrons. So representative nonmetals gain valence electrons to try to become S2P6. And then representative metals lose all of their valence electrons to become like a noble gas, right? So this is not like a noble gas. It's 2s2. Now it is like a noble gas. Same thing here. This is not like a noble gas. It's S2P4. If it gains 2 more, it becomes S2P6 like a noble gas. So now these two are stable. And then with non-representative metals, you do the same thing. The only issue is that you may not lose all of your valence electrons. Because remember, they don't follow all the rules. They try to. So here's iron in group 8. If it forms the +2, and the only way you would predict that is to look at the oxidation numbers on the periodic table, which is this. So it's got 8, loses 2, it's still got 6 left over. We don't have to explain that. It's just how it is. So here's a whole bunch of summary examples. Hopefully this is helpful and you read through that. And yeah, I guess that's it. So does anybody have any questions on chapter 8?
So for the number of valence electrons, going from left to right on the periodic table, is it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1, 2, 3, 4, 5, 6, 7, 8?
No, we use the Roman numerals for the valence electrons.
Oh, so like iron, cobalt, and nickel all have 8.
Yes.
Yeah. Okay.
Yep.
And then copper goes back to 1.
Yes, it does. Zinc would be, nitrogen would be 5, right? Yeah, I remember in chapter 11, I was trying to explain why there's so many different versions of the periodic table. And of course, if you're going to sell a periodic table, you want to have as much people buying it as possible, so you'd make it for everybody, right? All it does, though, really is make it confusing. Okay. Any other questions on this chapter? Okay.
So all the elements on the periodic table, like them alone by itself, they don't have a charge, correct?
Right. That's periodic table of the elements.
Right.
Elements
Like
are all neutral.
they're all neutral. They're all neutral, but they all want to become a noble gas. So then they'll become charged, or they'll become an ion, either positive or negative, to become that noble gas.
Yeah.
But my question is still about like, you know, like the 8, like number 8, like iron and like ruthenium and stuff. Like how would they become a noble gas? There's no way, right?
There's no way. That's why they don't follow all the rules.
But they still have 8 electrons. I mean, they still have 8 valence electrons.
Yes, they do.
So they are, but they're not stable.
No.
In a sense.
Remember, there's 2 ways. If you have no way to get like a noble gas, there's 2 ways to respond. One is you don't do anything.
Right.
And the other is you just oscillate back and forth between different ion states, right?
Yeah.
We can't really predict that, but we do, from observation, we can still deal with it by looking at the oxidation numbers. You know, so look at iridium, for example, right? Iridium is element number 77. I wouldn't be able to predict what it can do because it's not going to be like a noble gas. But what it does do, if it does anything, it forms the +3 and the +4 ion. But it doesn't get it to a noble gas electron configuration.
Yeah. So when it becomes a +4, that means it gives away 4 electrons, and that's just what it typically does, basically.
Yeah. Yep. If you force it to do it.
Mm-hmm.
Mm-hmm.
Okay.
For something like iridium, you basically have to put it in nitric acid and stuff like that to make it dissolve. Otherwise, it won't react. Okay, so we got one more chapter to review. Come on. Okay, so chapter 9 is about chemical bonds and how compounds are formed and how to name them. So I started off by just saying we got metals and we got nonmetals, right? 2 different kinds, 2 different behaviors. What if you take a metal and a nonmetal and put it together? Well, then you get ionic bonds. And we can understand why that happens. I did it with Lewis dot structures, and I did it with electron configurations. Why does magnesium want to form the +2? Because that's what it wants to do. Because when it loses those 2 valence electrons, it is like a noble gas. It does not become neon because it has different numbers of protons. Then chlorine is S2P5. If it gains an electron, it's S2P6. It becomes isoelectronic to argon. So now the metal ion and the non-metal ion are oppositely charged, so they're attracted to each other because of their opposite charges. What happens if you take a non-metal and a non-metal together? Well, they both want to take electrons, so they end up having to share them. So that's the whole concept there. So notice that these are empty, or not full p subshells, right? Here's the p orbitals that are not full. If I push them together, so here's the 2 nuclei right here. When it forms a bond, here's again the 2 nuclei right here. I have this huge volume where these 2 electrons are being shared. So this atom is attracted to that shared valence electron cloud. So is this. And that's the nature of the covalent bond. The atoms themselves are repelled by one another, but they're both attracted to the electron cloud in the middle, called the covalent bond, because that's what makes them electronically stable. So just to be clear, we're talking about atomic orbitals, not, in chapter 8, we're not talking about molecular orbitals. I tried to give you a little bit of an insight into how atomic orbitals turn into bonding orbitals called hybridized orbitals. But again, that's not going to be on the test. Then finally, the other combination is simply a metal with a metal. So that would be a metallic bond. And it's similar to the covalent bond in the sense that this cation is attracted to this electron cloud. This cation is attracted to that same electron cloud. And that's what holds it together. Then oxidation numbers are given on the periodic table. So here's an example using nitrogen, what the different numbers could be used for. So if it's going to do a negative, if nitrogen is going to do a negative, that means it's got to be attracted to something that's positive. But if nitrogen is going to be a positive, it has to be attracted to something that is relatively negative. And then redox reactions, simply know what is oxidation, know what is reduction. If you see one oxidation number change, that means it's a redox reaction. So here's using the oxidation numbers to get the formula for compounds. So besides simply being able to get the oxidation numbers off the periodic table, the only other thing is make it into a neutral compound. And the way you do that is you simply bring the charges down and then ignore whether they're positive or negative. So when we do covalent compounds, we do the same thing. But now we don't have a metal that we know is going to be positive and a non-metal that we know is going to be negative. So to figure out which one is positive and which one is negative, we'll look at electronegativity values. That's on side 2 of the periodic table. So here, chlorine is 3.16, sulfur is 2.58. So that means that chlorine is going to be the negative, sulfur is going to be the positive. So here's the only positive sulfurs. Here's the negative chloride. And then what do we have to do? Is simply cross these down and make the neutral compound. I don't know why. Okay, I think I should fix that, because what's happening is the sulfur is being oxidized, but the chlorine is being reduced. These are too far apart right here. I'll have to fix that. So here's several examples, getting the neutral compounds. And then we had to name things. So first look at the composition before you just start jumping in and naming it. Is it a metal and a non-metal, or is it all non-metals? Because that's how you choose the style. And so if it's a metal and a non-metal, it's going to be similar to sodium chloride if there's only one oxidation state, like magnesium. But if there's more than one oxidation state, you have to say which one it is. So why do I know that this is titanium 4 right here? It's because this 4 that's down here came from up here. And this 1 that's down here, not written, came from up here. So this is a combination of the titanium 4 ion and the chloride 1 ion. So I hope you never forget this. Dihydrogen oxide is the systematic name for water. So then I gave a whole bunch of different examples, lots of examples. And then your problem may be memorizing the polyatomic ions. Okay. So there's 19 of them. I gave you a couple of ways to help you memorize them. And just because they're in this chapter doesn't mean they're not going to be in other chapters. These things are all the way into the second semester of biochemistry, which is biochemistry 341. It's everywhere. Okay, so here's naming covalent compounds, and then finally, when we do ionic compounds, we always take the lowest ratio of cation to anion. Because if we didn't do that, then for example, every size crystal of sodium chloride would have a different formula. So that's called the formula unit. And we do a similar thing with covalent compounds. We have the empirical formula, which means that it came simply from the data. And the molecular formula is from further data that tells us how big the molecule is, or what atom is bonded to what atom. So the molecular formula is the thing that actually exists. Empirical formula may or may not exist, but it's similar to formula unit. It's simply the lowest ratio of one to the other. So a bunch of summary exercises, and then all this other stuff that won't be on the exam. But I was just trying to make you think. Trying to make you think as a scientist, essentially. That's the goal. So this one, for example, really, I look at my wife. She's a very smart, educated person. She's got 2 master's degrees and 2 PhD degrees, all in education. And she still goes back to her third world country of, if you're sick, salt and honey is what she takes. And so as a scientist, my tendency would be, well, that's not going to do anything. But I don't diss it because there are studies out there that shows you that this stuff actually works. So we cannot discount superstition. We have to find out, do the experiments, get the data. Does it really work or does it not? Then this whole thing about, is your information reliable? Unbelievable. So I went into some very controversial areas and tried to get you to think about where are you getting your data. Matter of fact, here's an interesting story. So yesterday we're all down at the beach in Waimanalo, and my son and his friends had stayed overnight there, and one of the guys there is a fairly new policeman, big guy. He's a guy you do not want to mess with, I'll tell you that. And it turns out we were talking, and I'm going to give him this data. He wants to see this data on guns and race and police actions and all this kind of stuff, because he's right there in the situation where it's happening. Obviously not so much in Hawaii, right? So we went through the whole thing. Anybody have any questions about anything? Any chapter, any topic? Okay. Well, I guess we'll stop here, and you may not go to the Zoom meeting at noon, but I will be there, continuing along in chapter 10. And by the way, if you have other questions during that lecture on chapter 10, don't hesitate to ask, okay?
So are we having for biochem? Are we having we're having our exam today?
Your exam is open today and tomorrow.
Okay. All right.
Yeah.
All right. Thank you.
Okay.
Sorry, what the exam? What the exam start today or tomorrow?
Today and tomorrow from 9 to 9.
For the chemical,
Hey, you
for
have,
chemical 100.
no, Chemistry 100 is next week.
Ah, okay, got it.
Yeah.
Thank you.
Sure. Okay, folks, well, I'll see you in less than half an hour. Okay, take care.
See you.